Hi there. In this video, I'm going to talk you through how we code the forward and Runge-Kutta method in Python to solve an initial value problem. So the first thing I'm going to do is import the NumPy library and also the matplotlib library. Okay, so these two libraries, what they are is NumPy for doing some numerical calculations, just helps for some arrays and also some functions which we're going to use which aren't intrinsic to Python. Matplotlib, this is so we can plot the solution. Okay, so first thing I'm going to do is, after I've done that, is I'm going to define what we call an RK4 function. RK4 is just a shorthand for the fourth order Runge-Kutta method. And in this, I'm going to have the four arguments f, t span, y0, and h. And I'll explain these in a minute. So within our RK4 function, I need to calculate the number of steps which are required. So we're going to use a constant step length, h. Okay, so we can work out how many steps we require to go from t-span or the start of t-span to the end by calculating the difference, dividing that by h, and then taking just the integer part so we have a whole number. The next thing I'm going to do is define two arrays for our solution. This is to contain the t values. Okay, so this is array of 0 to start with. The 1 is for the initial value of t, and then we've also got the number of steps which we're going to calculate to go from t0 up to the upper band of t. And y, I'm going to do similar, but I'm going to have a 2D array. And this is going to have n steps plus 1 rows by however many, or the length of y0. Okay, so what I'm going to do is I'm going to write how many length of y0. It's essentially how many equations I have in our ODE system. So I'm going to call that m. Okay, and we've set the first value of t to the first value of t-span. Oops. And we set the first row of y to be our y0. So those are our initial values for the initial value problem. Okay, now we need to step through the steps. Okay, so now in range, and we have n steps. So this is our for loop, and within the for loop, I'm going to calculate what we call stage values. Okay, now for a bit more of an explanation of these, I suggest you have a look at the lecture notes. But the fourth order Runge-Kutta method has 4 stage values, and these use so f of tn is going to be our ODE function. And within, for each stage values, we have different, oops, I've got 0.5. We have slight changes to t and y. Okay, again, for more details of that, see the lecture notes. Oop, forgot to multiply 0.5 by h there. Okay, K2. Okay, so you notice K2 and K3 are quite similar. And finally K4. So, and also you notice each of these K1, K2, K3, K4 require the previous stages to have been calculated. So this is what's called an explicit Runge-Kutta method. Okay, so that's the 4 stage values. So what we can now do is calculate the solution at the next step, which is the solution at the current step plus the step length divided by 6 and multiplied by a weighted sum of those stage values. Oops. Okay, so that's the fourth order Runge-Kutta method. We also need to update our t array, which is tn plus 1 is equal to tn plus h. Okay, so this is our RK4 method, and last thing we need to do in this function is to return the arrays t and y. Okay, so this is we've coded up the function, so what we now need to do is actually give it a problem to solve. So I'm going to use the simple problem from the lecture notes, which is just our ODE function is t times y. So I'm just going to put a little comment there saying define ODE function. Okay, and now we're going to define the initial value parameters. So this is things like what's the t-span. So for this example, I'm going to go from 0 to 1. what's our initial solution? So in this case, I'm going to say our initial solution is 1. Because we've only got one ODE, we've only got one ODE in our system. If this was a system of ODEs, we'd have a list of initial values here. But because we've only got one, I've just got one value, and we're going to use a step length of 0.2. Okay, so we've defined the ODE function, we've defined the parameters. Now all we need to do is solve the initial value problem, and to do that, we have our outputs are t and y. That equals to the name of our function. Actually, I could just copy and paste this here. Okay, so that's the name of the ODE function. T-span, y0 and h are defined here. Okay, at this step, I'm just going to run the code just to check any errors, and you can see I do have an error here. Yeah, so the error I've got here is I just go up. I've got m equals length y0, but here I only defined y0 as a number. So this is quite easily fixed by, let's put that into a list. And if I run that, you can see Python is now happy. Okay, so I've solved the IVP, but I don't know what the solution looks like. For simple examples, what I like to do is print table of results, or print solution table. And this is just so I can see what the solution looks like. So it's quite easily done with print statements. So I'm going to print a column of t values against a column of y values. Okay, so that's my column headings. And now what I'm going to do is I'm going to loop through each t value and print out tn against yn. And to do this, I'm going to use formatted print. So that's the f before my string. And I'm going to print 2 to say, let's say I'm going to print it to 2 decimal places. And I'm going to print y n. I'm going to print that to, let's say, 6 decimal places. Okay, that's arbitrary. I just want it each one to print the same number of decimal places. One thing you should note here is y is a 2D array, so you can see I've got the nth row, and here I've only got one column, so that's just the first column there. Okay, if I run that, got an error. Unsupported string. Yes, so here I was trying to print the whole t array. I should have said tn. Okay, and you can see there I've got a nice little table of results, and that can be used to compare against exact solutions if they're known, for example. Okay, so the last thing I'm going to do in this video is just also to plot the solution. Okay, so to do that, remember at the beginning we imported matplotlib. Okay, so I'm going to use that to plot our solution, and to start with we have to create a figure and axis objects. Okay, so the easiest way to do that is to fig, ax equals plot plt.subplots. And now all I need to do is plot t against y, and I'm going to use a blue line with circle markers. Okay, and I'm also going to give it a label, and this is the RK4 solution. Going to give it a couple of axis labels. Okay, so on the horizontal axis I have a label of t, and on the vertical axis, which is the y label, I'm going to have yt. And you can see here matplotlib accepts LaTeX equations. I'm also going to add a legend. Okay, we've only got one plot here, but sometimes legends are useful. And finally I'm going to show the plot. Okay, and you can see we produced a plot of our solution. So we've got the axis labels as well, and we have a legend here. If you look in the lecture notes, if you read further through, we can actually plot multiple solutions. So for example, the Euler method again and the RK4 method against the exact solution as well. But I hope this video helps you getting started with coding up Runge-Kutta methods.